Okay, so what I want to look at today is a parallel circuit. So a parallel circuit, you can see the flow of electrons here, and there are junctions where there's an option for the electrons to either move down this way or continue on and move down here. In this case, there's a third option, and to pass through these resistors. Now, I didn't put light bulbs, but I could have very easily put light bulbs. I just put these resistors on. And because that's kind of what the diagram will look like. So if I were to convert this over to a diagram, it'll look like this. Okay, so that's kind of pretty cool. Or we've got the symbol for the resistors. Okay, right now I have each resistor set at 10 ohms. Okay, and the battery set at 9 volts. The thing with parallel is that the current is not always the same. In series, current equals current equals current. But in parallel, you can see that it's not the same. Current is the flow of electrons. So you can see even right here, the flow goes along at a certain speed, and then, boom, it is definitely going faster through here. Over at the far end is super slow. So if anything, empirically, you could just see that the current is not going to be the same throughout. Okay, now the voltage may not be as obvious, but voltage, let's get our voltmeter out, and if I take a look here, hook it up, I'm going to have 9 volts show up. And if I were to show up or connect it over here, it'd be 9 volts showing up. Now you may be saying, well, isn't that because the resistance is all the same? Well, let's take this resistor, and I can slide this to change the amount of resistance. So if I crank up the resistance, the voltage here, you see, stays the same. Take a look at the speed in which these electrons are now going through. Very, very slowly. Let's crank it right up. And they're going super slow. Okay, and that's because there's more resistance. The more resistance will affect the current. But you've got 9 volts going through each of these resistors. So from that, we can have a set of rules. So our rule would be that the total voltage is equal to the voltage at 1, and which is equal to voltage at 2, which is equal to voltage at 3, no matter how many resistors you had. Now the current, let's say the total current, is equal to the current at the first resistor plus the current at the second resistor plus the current at the third resistor, and that would apply to however many you had going. This is very much like what we had in series, but kind of reversed. So this is parallel. Okay, and if you remember, let's put over here, this is what we should already know. In series, we had the voltage total is equal to V1 plus V2 plus V3, etc. And then the current was equal to current, which is equal to current all the way through. And so this is what we were coming from, and this is parallel now. We're learning, and you should see that the voltage is the same here. So what about resistance? Well, we had it where resistance, the total resistance, simply enough, was the sum of the resistors. But in parallel, it's a bit more complicated. We end up doing 1 over RT is equal to 1 over R1 plus 1 over, it's the inverse, right, over R2 plus 1 over R3. And that gets a bit more complicated, as you can imagine, because not only do we have to add up these fractions, at the very end we need to do an inversion here to get what RT actually is equal to. Fortunately, we can find out R through using Ohm's law. So if we had the voltage and we had the total current, we would have this, and then that would be able to solve for RT. Okay, so we end up saying RT is equal to the voltage divided by IT. Okay, so if we can apply that, then we can kind of avoid all this all this mess here. This is a much more simple mathematical operation, less chance for errors than it would be to go through all this. But they would, if you wanted to double check, they would give you both the same answer. Okay? All right.